If the angle of shear is 30 degree for a cubical body and change in length is 250 centimeter, then the original length of the cube is. So this is very simple, right? So we know shear stress is given by tan of theta. What is tan of theta? The shift in position of a layer. Okay, or you can say change in length. It's not change in length per se, it is shift in position of a layer. Okay, but they are calling it change in length. So it is x divided by L, and you want to find out L. Okay, so this is very simple, very straightforward. So it is tan of 30 degrees. Okay, so how much is tan of 30? Equals to x upon L, and you want L. So it is x divided by tan of 30 degrees. Okay, so sine 30 is half, cos 30 is root 3 by 2. So tan 30 is 1 upon root 3, right? So this is equal to x is 250 centimeters multiplied by, okay, dividing by 1 upon root 3 is equal to multiplied by its reciprocal. So multiplied by root 3. And all answers are in meters. So let's convert this to meters. Okay. So it is 2.5 meters multiplied by root 3. Root 3 is 1.73. So how much would be 2.5 multiplied by 1.73? Little less than 5, you can say. Okay, so option D, right? It's equal to 4.3 meters. So this was simple question. Next question. This is from NEET 2020. Okay. So a wire of length L, area of cross section A, is hanging from a fixed support. The length of wire changes to L1 when mass M is suspended from its free end. The expression for Young's modulus is. See, this is from NEET 2020. Okay. So recent question. So what is Young's modulus? It is MGL divided by A multiplied by delta L. What is delta L? It's change in length. The change in length is equal to original length is L, final length is L1. So how much is change in length? L1 minus L, right? So delta L is L1 minus L. What is the answer? They have taken M capital. So MGL divided by A multiplied by L1 minus L. Option D is the answer, right? So this kind of simple questions are still being asked. Next question. Two wires are made of same material and have same volume. There are two wires, they are made up of same material, they have same volume. The first wire has cross-sectional area A and second wire has cross-sectional area 3A. If the length of first wire is increased by delta L on applying force F, how much force is needed to stretch the second wire by the same amount? Okay, this is the question. Two wires have same volume. Okay, so volume of two wires is same. So V1 is equal to V2. So now, if this is a wire, this is area of cross section and this is the length of the wire. So volume can be written as this area multiplied by the length. Okay. So now for first wire, you can say it is A1 multiplied by L1, and for second wire, it's A2 multiplied by L2. So L1 upon L2 is equal to A2 upon A1. This is what we get, right? So see, this thing is given. Area of first wire is A, area of second wire is 3A. So this is equal to 3A upon A. Okay, so that is L1 upon L2 is equal to 3. This is given. Okay, I mean this is what we can find out from the given thing. Then we want to find out, actually this thing is given that change in length is same. Okay, if length of first wire is increased by delta L on applying force F, how much force is needed? This is the question. To stretch the second wire by the same amount. So see, we can use this formula, y is equal to mgl divided by A into delta L. Okay, and delta L can be written as then mgl divided by ay. Okay, delta L can be written as delta L, if you take it on left hand side, y on right hand side, so it can be written as mgl upon ay, and this is given that delta L1 equals to delta L2. Okay, so in place of mg, let's write F. Okay, because force is given. So let's write delta L1 equals to delta L2. So this can be written as F1 into L1 divided by A1 into Y. Okay, F2 multiplied by L2 upon A2 into Y. So Y and Y will get cancelled because it's the same material. So for same material, Young's modulus will be same. Okay, so Young's modulus does not depend on the length and area, etc. It doesn't depend on dimensions. It is property of a material. Okay, so A and A gets cancelled. So what do we get? So we can move A2 and L2 on left hand side, F1 on right hand side. So what do we get? F2 divided by F1 is equal to, okay, if I move this on right hand side, so it is equal to L1 upon L2 multiplied by A2 upon A1, right? So this is equal to, how much is L1 upon L2? 3. How much is A2 by A1? It is also 3, equal to 3. Okay, so 3 times 3 is 9. Okay, so this gives F2 is equal to what? It is 9 times F1. Okay, so answer is 9 times F. Option A. Is it clear? So let us see next question. The bulk modulus of spherical object is B. If it is subjected to uniform pressure P, the fractional decrease in radius is. This is the question. It's a simple question. Bulk modulus can be written as what? It is pressure multiplied by, okay, volume upon delta V, right? Or we can say it is equal to minus of P divided by delta V upon V. Okay, so we want to find out fractional decrease in radius. Okay, we want to find out fractional decreases in radius. So let's take delta V upon V on left hand side, B on right hand side. So what do we get? Minus of P upon B. Delta V upon V is minus of P upon B. Okay, so now this is a spherical object. What is volume of a sphere? Sphere V is equal to 4 by 3 pi r cube. Okay, so now let's recall from units and dimensions. So delta V upon V will be equal to what? It is equal to 3 times delta R upon R. because V is directly proportional to R cube. Okay, so delta V upon V is 3 times delta R upon R. So I can substitute 3 times delta R upon R over here. It's equal to minus P by B. Now take that 3 on other side. So what do you get? Delta R upon R is equal to minus P by 3B. This is the answer. Okay, option C. So the minus sign is not there because only magnitude is asked. Okay, how much will be the fractional change in radius? The magnitude of fractional change is asked. That's why it's P upon 3B only. Let's see next question. The Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from the same roof. Okay, so roof is also same. If we want the lower ends of wires to be at the same level, we want lower ends of these two wires at the same level, then the weights added to the steel and brass wires must be in the ratio of. So this is simple. Very simple question. Okay. Young's modulus of steel is twice that of brass. So let's use S for steel, B for brass. Okay. So now you have those two wires. Okay. And you hang some weights by those two wires. And you want extension to be same, extension to be equal. See, so extension can be written in terms of Young's modulus like this. Okay, so Young's modulus is F into L divided by A multiplied by delta L. Okay, Y equals to F into L upon A multiplied by delta L. So we can write delta L equals to, okay, if we take delta L on this side, Y on other side, F into L upon AY is delta L. So we want delta L of steel equal to delta L of brass. Okay, so this can be written as FL upon AY equals to FL upon AY. So let's put suffix S and here B. Okay, right? So now what's given? They have same length and same area of cross section. So we can cancel out length and area of cross section because it is same. Okay, so then Young's modulus of steel is twice that of brass. Okay, what is given? Young's modulus of steel is equal to 2 times Young's modulus of brass. This is given in the question. Okay, let me read it once again. The Young's modulus of steel is twice that of brass. This is given. Young's modulus of steel is twice that of brass. Two wires of same length and same area of cross section, one of steel and another of brass, are suspended from same roof. Okay, so there are two identical wires, but one made up of steel, another made up of brass. They are connected to same roof. Okay, if we want lower ends of wires to be at the same level, so you want same extension in those two wires. Okay, then the weights added to the steel and brass wires must be in the ratio of. This was the question. Okay, so Y can be written as F into L upon A into delta L. So if you want delta L, take delta L on other side, Y on right hand side. So delta L equals to F into L divided by AY. Okay, and you want same extension in both the wires. So Fs into, okay, you can write delta L equals to F into L upon AY. So put suffix S for steel and B for brass. Okay. Then the wires are identical. That means length and area of cross section is equal. So length and area of cross section can be cancelled out on both sides. Okay. So now Young's modulus of steel is 2 times that of brass. It is given. Okay. So you can cancel out this thing also, but factor of 2 will come there. Okay. So Fs divided by 2 is equal to Fb. Okay. So weights added to the steel and brass wires, they are in the ratio. So Fs upon Fb is equal to what? 2 upon 1. They are in the ratio 2:1. This is the answer. Option D. Is it clear? Next question. The appropriate depth of an ocean is 2700 meters. The compressibility of water is this thing. Okay. So compressibility we're going to discuss tomorrow, but it is just a definition. Compressibility just inverse of the bulk modulus. Okay, nothing else. Okay, so the compressibility of wire is 45.4. Sorry, compressibility of water, not wire. It is this much, and density of water is this much. What fractional compression of water will be obtained at the bottom of ocean? Okay, depth of ocean is given. We want what compression of water will be obtained at the bottom of ocean. So see, this is again, this is simple. Okay, so what is bulk modulus? It is equal to minus of P divided by delta V upon V. You want delta V upon V. Okay, so delta V upon V is equal to what? Minus of P upon V. Okay, minus of P upon V, and 1 upon B is what? 1 upon B is compressibility. So this is equal to delta V upon V is equal to what? Minus P upon compressibility is denoted by K or kappa, you can say. Okay. So minus P times K, and pressure can be written as, so delta V upon V is equal to minus of pressure can be written as rho g h, right? Pressure can be written as rho g h. Okay. So we can substitute values now. So density is given 10 raised to 3. Acceleration due to gravity is 9.8. Let's take it 10. Multiplied by height is 2700 meters, 2700. Multiplied by kappa is how much? It is 45.4 multiplied by 10 raised to minus 11. Okay. So this is 10 raised to 3, 4, 5, 6, right? So it is minus of 10 raised to 6 multiplied by 10 raised to minus 11 multiplied by 27 multiplied by 45.4. So approximately, I'm sorry, this will be little bit over 1000. Okay, but options are closed. So you have to calculate it. There is no option. Okay. Anyways, so 45, let's multiply, let's skip 4. 45 multiplied by 27. Okay. So how much would be this? 7 fives are 30. Sorry, 35, not 30. So 5 twos are 10, 13, 0, then 27 fours are how much? 108. Right? Am I right? I think so. So this is 5. Okay. 1215. All right. So this is 10 raised to minus 11 multiplied by 10 raised to 6. It's 10 raised to minus 11 plus 6. That is 10 raised to minus 5. Okay, 10 raised to minus 5 multiplied by this thing, this factor. So it can be written as 1.215. Okay, 1 point minus of 1.215 multiplied by 10 raised to 3. Right, this thing can be written as 1.215 multiplied by 10 raised to 3. Then we have multiplied by 10 raised to minus 5. So 10 raised to 3 minus 5 is minus 2. So option A is the answer. Right? Yes. Oh, you already calculated. Good. So option A is the answer. Okay. So let us stop here. Okay. And remaining part we'll discuss tomorrow. Right. Let us discuss these questions. Copper of fixed volume V is drawn into wire of length L. When this wire is subjected to a constant force F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? So we want to find out which of these graphs is a straight line. Okay. Okay. For a question based upon elasticity, always start from Young's modulus. Okay, you have some extension, some length, etc., etc. We can start with Young's modulus. So Young's modulus is F upon A multiplied by L upon delta L, right? So now if I move this delta L on left hand side, what can I say? Delta L is equal to F upon A multiplied by L upon Y, right? But see, delta L here will be proportional to L if all of the other quantities are constant. Okay, if all of the other quantities are constant, we can say that delta L is proportional to L. So see what is constant. So copper of fixed volume. So volume is constant, not the area, right? So area is not constant. Okay, it is drawn into wire of length L when it is subjected to constant force F. F is constant, Y is constant, but A is not constant. But what is constant? Volume is constant. So let us adjust volume there. Okay, so let's adjust volume. So we have F upon A multiplied by L. Okay, so I'm multiplying denominator by L. So I have to multiply numerator also by L, right? So then what do I get? I get F upon Vy, V is volume. Okay, now all of these things are constant. Okay, so what do you get? Delta L is equal to this constant multiplied by L square, right? So it is equal to this constant multiplied by L square. Okay, so if you take ratio of delta L to L square, it is a constant, or delta L is equal to constant multiplied by L square. That means if you plot graph between delta L and L square, it will be a straight line. Okay, so this is the question. Which graph is a straight line? So this graph is a straight line. Graph between delta L and L square. Next question. The following four wires are made of same material. Which of these will have largest extension when the same tension is applied? This is the question. Okay. So length and diameter of four wires are given. Which of them will have largest extension? This is the question. When same tension is applied. Okay, let's try to solve this. So we know that y is equal to f upon a multiplied by L upon delta L. So delta L can be written as F upon Y. These two are constant. Okay, same tension is there. Multiplied by L upon A. And A can be written as what? Pi r square. Right? We have diameters in the options. So we'll adjust diameter there. Okay. So we want diameter square. So we'll multiply this r square by 4. Okay, and we'll divide by 4. So this is equal to 4 upon 4f upon pi y. Okay, this is a constant multiplied by L upon diameter square, right? So delta L is directly proportional to length, inversely proportional to d square. Okay, so let's put the values. First one, so it is 200 divided by 2 square, that is 4, right? So this is some constant, let's call it k, and we just have to find out this factor now. Okay, L upon d square. Okay, so 200, we don't care about units because units of all the parameters are equal in all options. Okay, so it is 200 by 4. First one is A is 200 by 4, 50. B is, okay, 50 means 50k. B is 300 divided by 9. Okay, so it is how much? It is 100 divided by 3, 33.3. C is 50 divided by zero point 0.5, right? So it is 500 upon 5. It's 100. And option D. Okay, option D is 100 divided by 1. Oh, so we are having tie here, right? Option D and no, it's 0.5 square in option C. So it is 0.25, right? So this will be 200. Okay, so option C would be the answer, right? So if my calculation is correct, I think it is correct. There is, okay, 0.5 square is 0.25, right? 5 multiplied by 10 raised to 1. Okay, 10 raised to minus 1. 25 multiplied by 10 raised to minus 2, right? Okay, this is clear. Simple question, right? But lengthy. Next one. If the ratio of diameters, lengths, and Young's modulus of steel and copper wires shown in figure are P, Q, and S respectively, then the corresponding ratio of increase in their lengths would be. Okay, so the ratio of lengths is P, length of steel upon length of copper is P, then Young's modulus of steel divided by Young's modulus of copper is Q. This is given. No, ratio of diameters is P. Okay, so ratio of lengths is Q. Ratio of Young's modulus is S, and ratio of diameters of the steel and the copper, okay, is equal to P. This is given, okay, and we want to find out corresponding increase in their lengths would be. So most of the times the increment in length. There are questions based upon increment in length only. Okay, so it's good to memorize this formula. Delta L will be equal to what? F upon AY multiplied by L, right? And A can be written as what? Pi r square, or we can write it as, we want diameters. Okay, so we can write 4d square, okay, and y will be there. So after that we just have to take the ratio. So delta L of steel and delta L of copper is 4 upon pi. This will be constant, right, into force acting on steel. Okay, so force acting on steel, it's here, it is, this mass is 2m, this mass is 5m. So total force on steel wire, it will be what? 2m plus 5m multiplied by g, that is 7m multiplied by g. Okay, so for now let's keep it as this. Force on steel, length of steel upon diameter of steel square multiplied by y for steel. I'm sorry. And I want to divide it by, okay, same thing. So 4 by pi, force of force on copper, length of copper divided by diameter of copper square multiplied by Young's modulus of copper. So it goes into the numerator. So diameter of copper square multiplied by Young's modulus of copper. So this thing gets cancelled. 4 by pi and 4 by pi. Okay, this thing gets cancelled. After that, what do we get? We have force on steel. So it is 7 mg upon force on copper is 5 mg. So is there 7 by 5? There are two options. Okay. Multiplied by length of steel upon length of copper. Okay. Multiplied by diameter of copper upon diameter of steel. And we have square of that. Multiplied by, you have Young's modulus of steel in the denominator and Young's modulus of copper in the numerator. Okay. So this is equal to 7 by 5. Length of steel upon length of copper is Q. So 7 by 5 multiplied by Q. Length of, diameter of steel upon diameter of copper is P. So we have reciprocal of that. So it's 1 by P square multiplied by 1 by P square and multiplied by, you have Young's modulus of copper upon Young's modulus of steel, and again you have reciprocal of that. Okay, so it's 1 by S. So 7 by 5 Q upon P square S is the answer, and it is option B. Two wire of same material having radius in ratio 2 is to 1 and lengths in so two wire of same material having radius in ratio 2 is to 1 and lengths in ratio 1 is to 2. If same force is applied on them, then the ratio of their change in length will be. So again, this is simple question, right? We just have to do like last question. So change in length is given by what? It is F upon AY multiplied by length. Okay. So for first wire, let's call it delta L1, L1 and A1. So A1 can be written as, okay, let's keep it as it is, and let's divide it by delta L2, which is equal to F. They are pulled by same force, right? So F is same upon A2 Y multiplied by L2. Okay, we are dividing these two. So FF gets cancelled, YY gets cancelled. It is the same material, and we get delta L1 upon delta L2 equal to A2 upon A1 multiplied by L1 upon L2, right? So what is A2 upon A1? It is R2 upon R1 square, because area is directly proportional to radius square. R2 upon R1 square multiplied by L1 upon L2. So what is L1 upon L2? Radius in the ratio is 2 is to 1 and length in ratio 1 is to 2. That means R2 upon R1 is also 1 is to 2. Okay. So it is 1 is to 2 square multiplied by 1 is to 2. 1 upon 2. Okay. So that is 1 by 8. 1 by 2 square is 1 by 4. 1 by 4 multiplied by 1 by 2. 1 by 8 is the answer. Option D. The Young's modulus of the material of wire of length L and radius R is Y. If the length is reduced to L by 2 and radius R by 2, the Young's modulus will be. Tell me the answer. Young's modulus of a wire is Y if length is reduced to L by 2, radius to R by 2. What will be the resultant value of Young's modulus? This is the question. It's property of material, okay, not a wire of particular length and radius. So it will remain as it is. Young's modulus is property of material. For a fixed material, it will be fixed. Okay. It does not depend on length or area of cross section, etc. etc. Next question. When a block of mass m is suspended by a long wire of length L, the length of wire becomes L plus L. The elastic potential energy stored in the extended wire is. Tell me. This is very simple, right? Direct formula. What is elastic potential energy? Half of load into extension, right? So it is half of mg multiplied by extension is L. Okay, mg multiplied by L. This is the answer. Okay, it is half of load multiplied by extension. That is mg multiplied by L. Direct formula. Okay, very simple. See, if we see NEET questions, no, recent NEET questions, 2019, there was 2020 question. Okay, so in this one at least you have to do some calculation. In this one also some calculation. Okay, this one also was little bit different. But from 17, this was 18. Okay, 20. The questions have been very easy, right? So this chapter, definitely there will be one question. Okay, I mean, how much? Definitely 99%, right? Because there have been one or two questions in the past. Okay, and question will be easy. Okay, next question. Wires A and B are made up, sorry, not made up. Wires A and B are made from same material. A has twice the diameter and three times the length of B. If the elastic limits are not reached when each is stretched by the same tension, the ratio of energy stored in A to that of B is. Tell me. A has twice diameter and 3 times length of B. So extension delta L in A is equal to what? It is F upon A, F upon AY multiplied by LA. So it's the same material and force is equal. Okay, they are stretched by same tension. So just area of cross section is different. So this is for A. Similarly, you can write an equation for B. So LB is equal to F upon AB into Y multiplied by, sorry, this is delta LB. Okay, extension. Right. Sanjay is saying option B. Let's check. So F and Y gets cancelled. It is LA upon LB multiplied by AB upon AA. So how much is LA upon LB? A has twice the diameter and 3 times length of B. So diameter is, sorry, length is 3 times and diameter is twice. Okay. So diameter of A is twice. That means AB is to AA is half square. Okay. Diameter square. So it is, yeah, 3 is to 4. Right. 3 by 4. This is the answer. Option B. Young's modulus of the material of a wire is Y. On pulling the wire by a force F, the increase in length is X. The potential energy of the stretched wire is, again, same question, different exam, same question. Tell me. Option. So option A, right? Potential energy is half of load into extension. Half of the external force multiplied by extension. Two wires of same material and same diameter have lengths in the ratio 2 is to 5. They are stretched by same force. Okay, same material, same diameter, lengths are in the ratio 2 is to 5. Then the ratio of work done in stretching them is. So again, this is also simple. So delta L is directly proportional to L, right? Okay, and lengths are in the ratio 2 is to 5. Okay, so work done is equal to half of force into extension. Okay, extension is directly proportional to length. So W1 equals to half of F into delta L1, W2 equals to half of F multiplied by delta L2. If you take ratios, then half F gets cancelled. Delta L1 upon delta L2 will be what? 2 is to 5, because length of the length ratio is 2 is to 5. Okay, so it is option B. I'm sorry, there was one more topic called Poisson's ratio. So let's see Poisson's ratio. So when you stretch a wire, what happens to the area of cross section? It decreases, right? So Poisson's ratio is the ratio of lateral strain in the wire to the longitudinal strain. Okay, so what do you mean by this? The ratio of lateral strain. Lateral strain is change in diameter per unit original diameter, or change in radius, you can say, per unit original radius. Okay, so it is delta D divided by D divided by longitudinal strain. We know it is, oh, It is longitudinal. I wrote longitudinal. I'm sorry. Okay. So delta L divided by L. But it will be with negative sign. Why there would be a negative sign? Because when the length increases, diameter decreases, right? Length increases, diameter decreases. Okay. So this is Poisson's ratio. Okay. So this very short topic was left. All right. So let's see this question. There is no change in volume of the wire due to change in its length on stretching. Volume does not change. The Poisson's ratio of the material of wire is, okay. So volume is constant. So volume is constant. Volume can be written as what? Pi r square multiplied by L, right? It can be written as pi r square multiplied by L. And we can write now from units and dimensions, we can write delta V upon V is equal to what? 2 times delta R divided by R plus delta L divided by L. Okay. And delta V upon V is 0. This is given. There is no change in volume. So what we can say is, okay, 0 is equal to 2 times delta R upon R plus delta L upon L, or delta R upon R is equal to minus half of delta L divided by L, because if you take this on left hand side, it will be 2 times delta R upon R equals to delta L upon L, right? Okay. And therefore if you take that 2 on the other side, actually minus 2 on the other side, delta R upon R equals to minus half of delta L upon L. And what do you want? You want delta R upon R divided by delta L upon L. Okay. And you want it with negative sign also. So if you take that negative sign here, delta L upon L in denominator, you get half. So Poisson's ratio is equal to this thing. It is half. That is 0.5. Option A. Metal rod is fixed rigidly at two ends so as to prevent its thermal expansion. If L, alpha and Y respectively denote the length of the rod, coefficient of linear thermal expansion, and Young's modulus of its material, then for an increase in temperature of rod by delta T, the longitudinal stress developed in the rod is longitudinal stress. Okay, so we already know this thermal stress, right? What is thermal stress? It is Y multiplied by thermal strain. That is Y multiplied by alpha delta T. Okay, so thermal stress, is it inversely proportional to alpha? No. Inversely proportional to Y? No. Directly proportional to delta T upon Y? So it's directly proportional to delta T, okay, but it's not inversely proportional to Y. So this is also gone. Independent of L? Yes, it is independent of L. So option D is the answer. Right, Sanjay. It's option D. Next question. Two rods of different materials with coefficients of linear thermal expansions alpha 1, alpha 2 and Young's moduli y1 and y2 respectively are fixed between two rigid walls. They are heated to have same increase in temperature, same increment in temperature. If the rods do not bend and alpha 1 is to alpha 2 is 2 by 3, then the thermal stresses developed in two rods will be equal when y1 is to y2 is equal to. Again, this is very simple question. Thermal stress in first one is equal to thermal stress in second one. So y times alpha delta T for first one is equal to y times alpha delta T for second one. Increment in temperature is same, so we can cancel it out. Okay, so we have alpha 1 is to alpha 2 equals to y2 is to y1, and this is given. This alpha 1 is to alpha 2 is 2 is to 3. That means y2 upon y1 is 2 is to 3. So y1 upon y2 equals to 3 is to 2. Okay, option C is the answer. Right. Okay, so that was the last question. All right. So here we have finished another chapter, small chapter, but some questions are, I mean, at least one question is asked, most probably, from this chapter.